Curve sketching. Let's begin with a quick review of several concepts we've previously discussed, specifically with regard to how they relate to the graph of a function. The sign of the first derivative of f is an indicator of whether the function is increasing or decreasing. The sign of the second derivative of f is an indicator of whether the graph of f is concave up or concave down. If f of x approaches a number b as x approaches either plus or minus infinity, then the line y equals b is a horizontal asymptote. Notice that there may be two distinct horizontal asymptotes. If f of x approaches either plus or minus infinity, as x approaches a number a from either the left or the right, then the line x equals a is a vertical asymptote. If f is continuous at a, and if the derivative of f approaches either plus or minus infinity as x approaches a from both the left and the right, then the graph of f has a vertical tangent line at the point a, f of a. If f is continuous at x equals a, and if the derivative of f approaches plus infinity as x approaches a from one side, while it approaches minus infinity as x approaches a from the other side, then the graph of f has a cusp at the point a, f of a. If f is continuous at x equals a, and if the two one-sided limits of the derivative as x approaches a both exist but are different, that is, if f prime has a jump discontinuity at x equals a, then the point a, f of a is a corner point. That is, it's a point where the slope of the graph makes an abrupt change. Example. Sketch the graph of the function f of x equals 5x cubed minus 3x to the fifth power. We'll begin by taking derivatives. The first derivative, using the power rule, is 15x squared minus 15x to the fourth. The second derivative, then, is 30x minus 60x cubed. Now let's go back to the function and factor and look at where the function is equal to 0. That will tell us the x-intercepts. F of x is equal to x cubed times 5 minus 3x squared, and therefore it's equal to 0 at x equal to 0, as well as at plus and minus the square root of 5/3. The first derivative factors into 15x squared times 1 minus x squared. So we see that the derivative is equal to 0 at x equal to 0 and at plus and minus 1. Factoring the second derivative, we obtain 30x times 1 minus 2x squared, which is equal to 0 at x equal to 0, as well as at plus and minus the square root of 1/2. So let's start by drawing our x and y axes, and placing an appropriate scale on each one, and plotting the x-intercepts of the graph of f. F of x is equal to 0 at minus square root of 5/3, positive square root of 5/3, and at 0. Now let's look at the first derivative and think about its sign. Since it's 15x squared times 1 minus x squared, the only time it's negative is when 1 minus x squared is negative. So we can see that if x is less than minus 1, f prime of x is negative, and if x is between minus 1 and 0, it's positive, and it's also positive between 0 and 1, and it's negative if x is greater than 1. The value of f at minus 1 is negative 2, so let's plot the point minus 1, minus 2, and indicate that the slope of the graph there is 0. The slope of the graph is also 0 at 0, and since f of 1 is 2, we'll plot the point 1, 2, and again indicate that the slope there is 0. Now let's look at the second derivative, 30x times 1 minus 2x squared. If x is less than minus the square root of 1/2, then f double prime of x is positive, because it's the product of x, which is negative, and 1 minus 2x squared, which is also negative. Between minus square root of 1/2 and 0, f double prime is negative, because the factor x is negative while 1 minus 2x squared is positive. Between 0 and the square root of a half, f double prime is positive again, because both factors are positive, and if x is greater than the square root of a half, f double prime is negative, because the factor 1 minus 2x squared has become negative again. The value at minus the square root of a half turns out to be minus 7 over 4 root 2, which is about negative 1.24, so we'll plot a point where x is minus the square root of a half and y is equal to that value. Also, f of positive square root of a half is roughly positive 1.24, so we'll plot a point at x equal to square root of a half and y equals that value. Now, if x is less than minus 1, since f prime is negative and f double prime is positive, we conclude that the graph of f will be decreasing and concave up. Between minus 1 and minus the square root of a half, f prime is positive while f double prime is positive, and so the graph is increasing and concave up. Between minus the square root of a half and 0, f prime is positive while f double prime is negative, and so f is increasing and the graph is concave down. Between 0 and the square root of a half, both f prime and f double prime are positive, and so the function is increasing and the graph is concave up. Between the square root of a half and 1, f prime is positive while f double prime is negative, and so f is increasing and the graph is concave down. For x greater than 1, both f prime and f double prime are negative, and so the function is decreasing and the graph is concave down. So now let's sketch the graph. The part of the graph corresponding to x less than 1 is decreasing and concave up, goes through the x-intercept at minus the square root of 5/3, and the graph becomes horizontal at the point minus 1, minus 2, which turns out to be a local minimum, because on the other side of that point, f is increasing. Also, the graph is concave up. The concavity changes at x equals minus the square root of a half. Function is increasing and the graph is concave down until we get to the point 0, 0, where the tangent line is horizontal. When x is greater than 0 but less than the square root of a half, the function is increasing and the graph is concave up. The function continues to increase while the graph is concave down between square root of a half and 1, and then when x is greater than 1, the function is always decreasing and always concave down. So here's the graph of our function. Notice that we have a local minimum at x equals minus 1, we have a local maximum at x equals 1, we have a critical point at 0 where there's neither a local max nor a local minimum. We have 3 inflection points corresponding to x equals minus square root of a half, 0, and positive square root of a half. Now let's remove the scaffolding here so we can see the graph with less distraction. Example. Sketch the graph of f of x equals x squared minus 6 times the cube root of x. Let's first notice that f of x can be factored into x to the 1/3 power times x to the 5/3 power minus 6, which tells us that the function is equal to 0 at x equals 0 and at the 3/5 power of 6, which turns out to be about 2.93. So these are our x-intercepts. So let's go ahead and plot those. Now let's find the first derivative. By the power rule, it's 2x minus 2 times x to the minus 2/3 power. Here, let's factor 2 times x to the minus 2/3 power from both terms, revealing a second factor, x to the 5/3 power minus 1. So we see that the derivative is undefined at 0, and it's equal to 0 at x equal to 1. Since the function is defined at 0, 0 is a critical point, as well as x equals 1. So let's think about the limit of f prime of x as x approaches 0 from both the left and the right. Notice that the factor 2x to the minus 2/3 power is never negative. So we only need to be concerned with the factor x to the 5/3 power minus 1. If x is close to 0, that factor is negative, so both of the one-sided limits as x approaches 0 of f prime of x are minus infinity. Therefore, we conclude that the graph of f has a vertical tangent line at x equals 0. The value of f at 1 is minus 5, so let's plot the point 1, minus 5, indicating a horizontal tangent line there. And let's also indicate that the tangent line is vertical at the point 0, 0. Now let's think about the sign of f prime of x. If x is less than 0, then f prime of x is negative. It's also negative between 0 and 1. If x is greater than 1, then f prime of x is positive. Now let's compute the second derivative. Using the power rule, differentiating f prime of x, we find 2 plus 4/3 times x to the minus 5/3 power. Let's factor 2 times x to the minus 5/3 power from each term, revealing the factor x to the 5/3 power plus 2/3. So now let's notice that f double prime of x is undefined when x is 0, as it should be because f prime of x is undefined there. And f double prime of x equals 0 at x equal to minus the 3/5 power of 2/3, which is approximately minus 0.784. So now let's think about the sign of f double prime of x. Notice that the factor 2x to the minus 5/3 power is negative when x is negative and positive when x is positive, and the factor x to the 5/3 power plus 2/3 changes sign at minus 2/3 to the 3/5 power, where the value turns out to be 10 times 2/3 to the 6/5 power, or roughly 6.15. So let's plot that point. And now let's think about the sign of f double prime. If x is less than minus 2/3 to the 3/5 power, f double prime is positive because it's the product of two negative factors. Between minus 2/3 to the 3/5 power and 0, f double prime of x is negative because it's the product of a negative factor and a positive factor. And when x is greater than 0, both factors in f double prime of x are positive, and so f double prime of x is positive. So now we can see that if x is less than minus 2/3 to the 3/5 power, f prime of x is negative and f double prime of x is positive, and so the function is decreasing and the graph is concave up. Between minus 2/3 to the 3/5 power and 0, f prime of x is negative, while f double prime of x is also negative, and so the function is still decreasing and the graph is switched to being concave down. Between 0 and 1, f prime of x is still negative, but f double prime of x has changed to positive, and so we know that the function is decreasing and the graph is concave up. If x is greater than 1, both f prime and f double prime are positive, and so the function is increasing and the graph is concave up. So now let's sketch the pieces of the graph. Here's the part of the graph to the left of minus 2/3 to the 3/5 power. Then, between minus 2/3 to the 3/5 power and 0, where the function is decreasing and the graph is concave down, we have the following. Notice the vertical tangent line at 0, 0. Then between 0 and 1, where the function is decreasing and the graph's concave up, we have this. And then to the right of 0, we continue the graph so that it's increasing, passes through our x-intercept while always being concave up. Example. Sketch the graph of f of x equals x cubed divided by x squared minus 3. Let's first notice that the denominator here is equal to 0 when x is equal to plus or minus the square root of 3. So we expect to have vertical asymptotes at each of those numbers. So let's calculate all of the one-sided limits as x approaches either plus or minus the square root of 3. If x is less than negative square root of 3, then the numerator x cubed here is negative, and the denominator is positive. Therefore, the limit as x approaches negative square root of 3 from the left of f of x will be negative infinity. If x is close to negative square root of 3 but greater than the square root of 3, the numerator here is still negative while the denominator is also negative, and so therefore the limit as x approaches negative square root of 3 from the right will be plus infinity. If x is slightly less than the square root of 3, then x cubed will be positive while x squared minus 3 will be negative, and so the left-sided limit as x approaches positive root 3 is negative infinity. If x is slightly greater than the square root of 3, then the numerator and denominator of f are both positive, and so the right-sided limit as x approaches root 3 of f of x will be plus infinity. So we see that both left-sided limits at our asymptotes are minus infinity, and both right-sided limits are plus infinity. Now let's calculate the derivative. We use the quotient rule. F prime of x will be a fraction whose denominator is x squared minus 3 squared, and the numerator is the derivative of x cubed, 3x squared, times the denominator, x squared minus 3, minus the numerator x cubed times the derivative of the denominator, which is 2x. Now notice that in the numerator we have a 3x to the fourth term, as well as a minus 2x to the fourth term, and so we have an x to the fourth, and then the other term is minus 9x squared. In factored form, that's x squared times x squared minus 9. So we can factor the numerator further and write x squared times x plus 3 times x minus 3 all over x squared minus 3 quantity squared. Now let's calculate the second derivative. The denominator is x squared minus 3 to the fourth power. In the numerator, we'll start with the derivative of x to the fourth minus 9x squared, which is 4x cubed minus 18x, times the denominator x squared minus 3 squared, and subtract x to the fourth minus 9x squared times the derivative of the denominator, which we'll obtain using the chain rule. It will be 2 times x squared minus 3 times the derivative of x squared minus 3, which is 2x. Now, before we multiply out the numerator, let's notice that we can factor x squared minus 3 from each term and cancel with an x squared minus 3 from the denominator, effectively lowering the powers on all of those factors. Now we expand the products in the numerator and simplify to obtain 6x cubed plus 54x divided by x squared minus 3 cubed. And factoring the numerator gives us 6x times x squared plus 9 divided by x squared minus 3 cubed. So now let's replace all this work with a summary of our results. The left-sided limit at each of the vertical asymptotes is minus infinity. The right-sided limit at each of the vertical asymptotes is plus infinity. Here's our derivative in factored form, and here's our second derivative in factored form. Let's now draw a pair of axes and place our vertical asymptotes, x equals minus the square root of 3 and plus the square root of 3. The critical numbers of f are the zeros of f prime, and these are 0 and plus and minus 3. At 0, the value of f is 0, so let's plot 0, 0, and indicate that there's a horizontal tangent there. The value of f at plus and minus 3 will be plus and minus 27 over 9 minus 3, or plus and minus 9 halves. So let's plot the point minus 3, comma, minus 9 halves, and indicate that there's a horizontal tangent there, and also plot the point 3, comma, 9 halves, where there's also a horizontal tangent. Now let's think about the sign of f prime of x. Notice that the x squared in the numerator of f prime of x, as well as the denominator, x squared minus 3 quantity squared, will not really play a role in determining whether f prime of x is positive or negative, since those can never be negative. So we really only have to look at x plus 3 times x minus 3. If x is less than minus 3, then both of those factors are negative, and so f prime of x will be positive. And we will not have another sign change until we reach x equals 3. When x is greater than 3, f prime of x becomes positive again. Now let's look at the second derivative. Notice that the only values of x where f double prime of x can change sign are plus and minus the square root of 3, as well as x equals 0. When x is less than minus the square root of 3, the numerator of f double prime is negative, and the denominator is positive, and so f double prime of x is negative. If x is between negative root 3 and 0, the numerator and the denominator are both negative, and so f double prime of x is positive. If x is between 0 and positive root 3, the numerator of f double prime of x is now positive, while the denominator is still negative, and so f double prime of x is negative, and then for x greater than the square root of 3, the numerator and denominator are both positive, and so f double prime of x is positive. So now we conclude that when x is less than negative 3, f of x is increasing, and the graph is concave down. Between negative 3 and negative root 3, f of x is decreasing while the graph is concave down. Between negative root 3 and 0, f of x is decreasing while the graph is concave up. Between 0 and the square root of 3, f is decreasing and the graph is concave down. Between the square root of 3 and 3, f is decreasing and the graph is concave up. And then finally, for all x greater than 3, f is increasing and the graph is concave up. So now let's sketch the graph. It's increasing and concave down until we reach a local maximum at x equals minus 3. Now, between that point and the vertical asymptote at negative square root of 3, we're decreasing and concave down, and the limit as x approaches negative root 3 from the left is negative infinity, and so we draw the graph like so. Now, between negative root 3 and 0, we use the fact that the right-sided limit at negative root 3 is plus infinity, as well as the fact that the function is decreasing and the graph is concave up, to draw this part of the graph. Then, between 0 and positive root 3, we use the fact that the function is decreasing, the graph is concave down, and the function approaches minus infinity as x approaches negative root 3 from the left. Then between root 3 and 3, our function is decreasing, the graph is concave up, infinity, and so we draw this part of the graph, and then we continue the graph for x greater than 3 in such a way that the function is increasing and the graph is concave up. Now we remark here that there's an additional structure in this graph which is often called a slant asymptote. In fact, for large values of x, the graph is close to the line y equals x. To see why this is so, notice that if we did long division on our function, we could rewrite it as x plus 3x over x squared minus 3. So for large values of x, the second term is very small, and f of x is approximately equal to x. In other words, the limit as x goes to either plus or minus infinity of f of x minus x will be 0. One last example. Sketch the graph of f of x equals x to the fifth plus x squared plus 1 divided by x to the fifth plus 1. Let's first notice that we can make our work a little easier. If we split the fraction into 2, as shown here, which allows us to write our function as x squared over x to the fifth plus 1 plus 1. Notice that the same thing could be accomplished by long division. This form suggests that y equals 1 will be a horizontal asymptote. That is in fact true. The limit as x approaches plus or minus infinity of f of x will equal 1. So let's draw our axes and place the horizontal asymptote at y equals 1. The fact that the denominator is equal to 0 when x is negative 1 suggests that x equals negative 1 is a vertical asymptote. That is in fact true, and the limit as x approaches minus 1 from the left of f of x will equal negative infinity, because if x is less than minus 1, the denominator of the fraction is negative, And the limit as x approaches minus 1 from the right of f of x is plus infinity, because if x is greater than minus 1, x to the fifth plus 1 is positive. So the line x equals minus 1 is a vertical asymptote. Now let's compute the derivative. F prime of x, using the quotient rule, will be a fraction whose denominator is x to the fifth plus 1 squared. The numerator will be the derivative of x squared, 2x, times the denominator x to the fifth plus 1, minus x squared times the derivative of x to the fifth plus 1. The numerator simplifies to 2x minus 3x to the sixth power, which then factors to give us x times 2 minus 3x to the fifth, all divided by x to the fifth plus 1 squared. So we can see that the derivative is equal to 0 at x equal to 0 and at the fifth root of 2/3, which is approximately 0.92. Now the value of the function at 0 is equal to 1, so let's plot the point 0, 1 and indicate that there's a horizontal tangent there. The value at the fifth root of 2/3 is approximately 1.51, so let's plot the resulting point and indicate that there's a horizontal tangent there. Now let's think about the sign of f prime of x. If x is less than minus 1, then the numerator of f prime of x equals a negative number times a positive number, and the denominator is positive, and so f prime of x is negative when x is less than minus 1. Between minus 1 and 0, it's still negative. When x is between 0 and the fifth root of 2/3, the factor x becomes positive, and so f prime of x on that interval is positive. And if x is greater than the fifth root of 2/3, the 2 minus 3x to the fifth factor becomes negative, and so f prime of x is negative for x greater than the fifth root of 2/3. Now let's compute the second derivative. Again, using the quotient rule, we have a denominator of x to the fifth plus 1 to the fourth power, and the numerator will be the derivative of 2x minus 3x to the sixth, which is 2 minus 18x to the fifth, times the denominator x to the fifth plus 1 squared, minus the numerator 2x minus 3x squared, times the derivative of the denominator, which by the chain rule is 2 times x to the fifth plus 1 times 5x to the fourth. Now to simplify, we'll first cancel factors, then expand the products in the numerator, which leaves us with 2 times 1 minus 18x to the fifth plus 6x to the 10th divided by x to the fifth plus 1 cubed. So let's now find out where f double prime of x is equal to 0. Using the quadratic formula, we can find the values of x to the fifth, which are 9 plus and minus 5 root 3 divided by 6. And the resulting values of x are the fifth root of 9 plus and minus 5 root 3 over 6. These numbers are approximately 0.563 and 1.24. So let's locate those on the x-axis. And calculate the value of f of x at each one. Those values are approximately 1.30 and 1.39, so we'll plot the two resulting points, and then examine the sign of the second derivative. If x is less than minus 1, then the denominator of f double prime of x is negative, while the numerator is positive, and so f double prime of x is negative. Now if x is between minus 1 and the smaller of the two zeros of f double prime, the numerator of f double prime is positive and the denominator is also positive, and so f double prime is positive. Then, between the two zeros of f double prime, the numerator is negative while the denominator is positive, and so f double prime of x is negative. And then when x is greater than the larger of the two roots of f double prime, the numerator and denominator are both positive again, and so we have positive values for f double prime of x. So, on the interval from minus infinity to minus 1, f of x is decreasing and the graph is concave down. Between -1 and 0, f of x is decreasing and the graph is concave up. Between 0 and the smaller root of f double prime, the function is increasing and the graph is concave up. Between the smaller root of f double prime and the critical point at the fifth root of 2/3, the function is increasing and the graph is concave down. Between the fifth root of 2/3 and the larger root of f double prime, the function is decreasing and the graph is concave down. And then between the larger root of f double prime and infinity, the function is always decreasing and concave up. So now let's sketch the graph, remembering the vertical and horizontal asymptotes. Here's the first part of the graph where it's decreasing and concave down and approaching minus infinity as x approaches -1 from the left. Here's the next section of the graph, approaching plus infinity as x approaches -1 from the right, and decreasing and concave up until we arrive at the point 0, 1. On the next interval, the function's increasing, the graph's concave up. Then the concavity switches to concave down while the function is still increasing. Then the concavity stays downward as the function begins to decrease. And then the function values continue to decrease while the graph is concave up as we approach the horizontal asymptote y = 1.